Welcome to 15.6, exponential growth function. So we're going to be applying the upwardly sloping functions, the ones that we're increasing from 15.4 to the real world. Now, for the next two lessons, you want a calculator. The better the calculator, the better for you. You don't need a calculator, but you want to pause the video and go get one. All right, so we got to remember how to do percents. So we're about to grow 10%. Now I'm going to do this two ways. Different teachers show different ways of doing this. So there are 400 students now, and there's going to be 10% more at the end of 1 year. So figure out that, some method. Well, let's understand what 10% is. 10% means 10 out of 100, right? 10% means out of 100. So 10% is 10 out of 100, also known as the fraction 1/10, also known as the decimal point 1. There's a nifty shortcut to turn a percent into a decimal. It's called move the decimal twice. You move it over there, you get rid of the 0 and the percent sign, and that always works. 10%, you move the decimal twice to the left, and you make the percent into a decimal. Once you remember that, 10% then of 400, right? We're going to move the decimal once, is 40. So there would be 40 more students than there were last year, or 440 students. So how many would there be at the end of 1 year? You don't say 40, there would be 440 students. Now, the way I teach my 7th graders is a little faster, right? 400 students is 100% of the students that were at the school. So if we're going to have 10% more than 100%, 10% more than 100% is 110%. So next year there'll be 110% more students. So you take 400, and now 110% as a decimal is 1.1. Right? A nifty shortcut, moves the decimal twice, turns a percent into a decimal. You can't multiply by 110. That's not a thing. So you do that multiplication, and look what happens. Move the decimal once, you go right to the answer. Either way works, but 10% more would be 440 students. All right, now answer the next question. Now some of you are thinking, well, it's 440, add 40 more, you get 480 students. And that is entirely wrong. All right. And the reason it's wrong is that's linear thinking. You're adding 40 every single year, but that's not what it says. It says that we're adding 10% every year. So that was 10% of 400. But at the beginning of this second year, there are 440 students. So we have to do 10% of 440, also known as 444. And so you would add those 44 students to the 440 you already have, and the correct answer is 484 students. Or done with the other method, it would be 440 times 1.1, right? And you get a 0.44, and you step over and you get a 0.0044, and you get the 484 students either way. Yes. So when you do the second and third year, you need the answer from the previous year. So as your parents have maybe told you, college increases in cost. It seems really fast. And the reason is because the cost of college, like a lot of things, increases exponentially, not linearly. Now we're going to see a bunch of other examples in the real world of that. Exponential growth functions. Okay, so bacteria and viruses, very topical, follow exponential rules. So let's look at this. We have one bacteria, and it can split into 2 cells every hour. So at time t, we're going to use t instead of x, tradition, because time. They're all in the real world. It's all about time. So at time 0, the beginning, all right, we're at 1, right? The y-intercept here is 0, 1, like it was for the easy ones we did that first day. So an hour later, there are 2. 2 to the first. 1 hour later, there are 2 of them. 2 hours later, there are now 4, right? The base here is 2. We're making 2 new ones, or the ratio is twice as much every single hour. So 3 hours later, we're at 8, 2 to the third. So where are we at 10 hours later? Well, f of t, f of 10, using this, the y-intercept was 1, so we don't even need to write it, but I will just to make sure you understand that. The base here is 2 because we're doubling every hour, and since we don't have a fraction base, we can put the t, and we're putting that 2 to the 10th. So it's 1 times 2 to the 10th. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128, times 2 is 256, times 2 is 512. 1, 2, 3, 4, 5, 6, 7, 8, 9. 512 times 2, 1,000. Oops, I should write times 2. So at 10 hours later, when you had 1 bacteria, now you have 1,024. Right? That is exponential growth. 2 to the 10th, because it's 10 hours later and it's doubling every hour, every time period. All right. So how do you get a lot of followers on Instagram? Through exponential growth. All right, so we have John tweeted, oh, this is Twitter. All right, so tweeted 3 friends a photo he thought was hilarious. So we have 1 person. All right. So we have 1 person. That's our y-intercept. But he's tweeting 3 friends, and a minute later, his friends are tweeting 3 of their friends. All right, if they tweet it back to John, it's slightly different. But we're going to assume 3 new friends, and they do the 3-minute friends, and so on. So it's tripling every time period. The time period here is not an hour, it's a minute. And so we want to know, in 6 minutes later, if everyone's doing that, how many people will see the photo? So f of 6 equals 3 to the 6th, or 3 times 3 is 9, times 3 is 27, times 3 is 81, times 81 times 3 is 243, times 3, 3 times 3 is 9, 12, 729 people, I guess it would be students, oh, friends, okay. 729 friends would see this photo within 6 minutes if everyone's tweeting 3 new people. That is a big assumption there, right? Because in the real world, some people tweet it back to someone who's already seen it. All right, so let's read this one. 7 bacteria placed in a dish. So the y-intercept here is 7, right? The first 2, the y-intercept was 1. We started with 1 bacteria or 1 friend. So we're going to do, so f of 7 here. Or, no, we're not doing f of 7, my fault. There's 7 bacteria. That's the y-intercept. Split into 2 new cells. So times 2, it's doubling every hour, times 2 to the t. And we're going to evaluate that for f of 5 hours. So it's 7 times 2 to the 5th. Right? You have to do the exponents first. Now notice I know the answer to this, like in my head. You really want to, for high school, have this in your head. This is the powers of 2. Right? I know 2 to the first power is 2, then 4, then 8, then 16, then 32. This is 7 times 32. And so we would have 224 bacteria 5 hours later, starting with 7. Many problems don't double or triple or quadruple but they do still go up exponentially. They go up a percentage. And that's what we're going to do. We're going to go back to that one we did in the warm-up. So in the warm-up, right, we said that we started with 400 students. Then we had 10% more. We multiplied it by 1.1. In year 2, if you take 440 and multiply it by 1.1, I showed you get 484. So now I want you to do year 3. We now have 484. If we have 10% more, it's going to be 484 times another 1.1, right? 100% is 1. 10% more than that is 110%, also known as 1.1. So we get 484. We step over. We get 484. We add up the 2 rows. And notice we get 532.4. Now, students hate to be 4/10, right? Now, you could leave the 0.4, but I'm going to round. I'm going to do a lot of rounding here so we don't go crazy with calculators, but it's 532 students. All right, so there's the 532 rounded, and now we're going to do, it says, at the end of 5 years, right? So we could keep going. We could do 532 times 1.1, and then put the 5th year, get that answer, and do 0.1.1. But we want a faster way. The faster way is exponential functions that you saw on the last screen. The y-intercept, so we're going to use t, all right? Y-intercept is 400. Right? And then each time we're multiplying by 1.1 to make it 10% bigger. So it's 100% plus 10%, also known as 110%, also known as 1.1. Our base here is 1.1 and to the t. So there is our function. So we're evaluating f of 5. So it's 400 times 1.1 to the 5th. Now, if you have a bad calculator, you're stuck, or don't have one at all, you're stuck doing a lot of 1.1s. But if you have a good calculator, there's a button that looks like this. And you type in the y, the base, the 1.1, and then you type in the x. So that's what I'm doing right now on my calculator. The iPhone, if you tilt your iPhone to the side, you get, oh, I bought on the iPhone, it's x to the y. Right, so you type in the 1.1, you hit x to the y, and then you hit 5, and you get 400 times 1.61051. And then 1.61051 times the 400, right? You had to do exponents first, right? At the end of year 5, we'd have 644.204 students, but once again, students don't like to be cut into fractions, and so we have approximately 644 students there, right? So we started with 400, and it's growing 10% every year. It's growing exponentially. It's not doubling or tripling, but it's going up by 10% every year. And so each number is based on the one before it. So now if you sit there and do 1.1 times 1.1 times 1.1, you'll get this. Okay, so let's try another one. A number of students in school is projected to grow 20% per year, right? So you start with 100% students, you add 20%, you have 120%. So how would you write that as a decimal? Right, so it's f of t. There are currently 600. That's our y-intercept at time 0, right? At time 0, we have 600 students. And it's growing by 1.2. The constant ratio is 1.2, and we're going to do, right, f of 7. So it's 600 times 1.2 to the 7th. All right, so I'm getting out my calculator, and 1.2 x to the y to the 7th is 3.583180. Right? You really don't want to do this without a calculator. times 600 equals, all right, times 600, and there will be, if they're growing 20% per year, there will be 2,150 students there at the end of our 7 years. Yeah, 20% growth is huge. All right, here's the college question. See if you can answer it without my help. So right now, it's about $60,000 per year. It totally depends on the college. Many are different. It's growing about 7% per year, which it was for many years. It's slowed slightly recently. And we want to know, right, we're in 8th grade. We're going to be ready to go to college in about 5 years. What's it going to cost then? All right, so we have to do 1.07 to the 5th. 1.07 to the 5th equals 1.40255. There's a bunch of other numbers I don't want to type, but it's a little bit more than 1.4. We multiply that times the 60,000 it costs now, and 5 years from now, your parents unfortunately can expect college to cost $84,153 per year. Yeah, exponential growth is not fun in many instances. Now, the good news for exponential growth is when you put money in the bank, they pay you your interest exponentially. All right. Now, if you've done interest problems in 6th or 7th grade, you've probably done simple interest, which is not what the real world does. And we're going to compare the two in a later screen. So let's see that. So you put money in a bank, right? They pay you for putting the money in the bank. They don't leave it in your bank account. They show the 4,000 there in your bank account, but they're actually loaning that money to other people at a higher interest rate. So that's what banks do. They get you to put their money there for safekeeping, and they pay you a little bit of interest. Now, this is on a savings account. On a checking account, all right, they don't pay you interest usually, but on a savings account, in other words, an account where you're going to put the money in it and leave it there. And if you take any of it out, the math is different. But you leave it in there, they're going to pay you compound interest. Now, when I was your age, the interest rate was 5%. Now it's around 1%. But let's do it for 5% because it's more interesting. 50, we're starting with 4,000. We're going to go up 5%. Now, 5% is 105%. So it's 1.05, right? Don't do 1.5. That's 50%. You wish you'd get that. And then we're going to say 2 years later. Okay, so it's 1.05 to the second. So 1. Now you could do that without a calculator. 1.05 times 1.05 turns out to be 1.1025. And we're going to multiply that times 4,000. And so 2 years later, there would be $4,410 in your account, right? You've done nothing. They've paid you $410 for leaving your money in their bank. That's called the interest, and it's compounded. If it was simple, right, 4,000 times 0.05, right, they would just pay you $200, and $200 twice would be $400. That's probably the way you did it in 6th grade or 7th grade, right? But in fact, in reality, they're paying you $10 more than that. And so banks pay compound interest, and it's always annual interest, although you can write the problems with the interest being calculated in other time periods. It's usually annually. Annually, if you don't know, means yearly, all right? So every year you get 5% more. All right, so try one on your own. and it's approximately 1.55. Mine came out a lot of digits. So notice you put $4,000 in the bank, do nothing to it, don't take any out, and I'm rounding this right to the nearest dollar, is you get $6,205 back after 9 years with 5% compound interest annually. All right, so let's compare compound interest to simple interest. All right, so notice the blue one is linear, simple. All right, so that's simple interest. And then the red one is compound, that's reality, all right? And that's exponential. So when in 6th or 7th grade you did interest problems, the reason you were able to do simple interest, because they're pretty close together in their first 4 years. They get farther and farther apart in these later years. Look how far apart those are as the curve starts to bend. All right, so let's do the compound interest. 4,000, right, so it's exponential if it's compound. So it's f of t, starting with that same 4,000, we're getting our 5%, and now it's 18 years later. All right, so let's see the difference. So 1.05 equals, so I have to do 1.05 to the 18th power, and notice I get around 2.4, and it's 2.4066, and it goes on forever, times, so I have to multiply that times the 4,000 that we started with, and 18 years later, you would have, in dollars, $9,626 approximately. Now let's compare that. So that's this point here. So here's 18, and this point here, right, these are going up by what? 200, 400, 6, let's see, 4,200, 400, now, what's it going up? Oh, it's 1,200 divided by 1, 2, 3, 4, oh, by 300. So 4,300, 4,600, yeah, they're going up by 300. So this is around 9,000, right, around 9,600. That's this line right here, 9,600, and this is 9,626. Okay, now let's look at the simple interest in blue there. All right, so the simple interest would be f of t, right? We're starting with a y-intercept of 4,000. Now, we're getting, instead of x, we're going to use t for our variable. So what is the slope of this line? Well, it's 5%. It's 5% of 4,000. And that is, we move the decimal, make sure I do this right. 1, 2, 3. No, I'm missing a 0. That's what I thought I did. And then 1, 2. Yeah, it's $200, right? 5%, if we were just doing simple interest, you'd be saying, oh, you get $200 every single year, right, for 18 years. So that's the linear function for simple interest, right? You're getting $200 more. That's our slope. That's the slope of this, right? Right? We're going up $200. Whoops, so that's not 200, right? You're going up $200 every year. How many? 1, 2, 3. So that'd be $600 in 3 years. Okay, we're going up $200 every year, and we're doing f of 18. So 200 times 18, and then you add that to the 4,000. What's 200 times 18? I'm getting my calculator out. So 200 times 18 is 3,600. And so if it was simple interest, the bank would only pay you 7,600. So that space between the red and blue line at year 18, that's the extra money. What is it? It's about $2,000. $2,000 extra because the bank is paying you compound interest. So this is very good news for savings accounts, and it's all contingent on you leaving there. But this is what smart people do. They put their money in the bank or some other investment, it doesn't have to be a bank, and leave it there. And they leave it there for a long time and just don't touch it. And when they come back, right, we started with 4,000 and now it's more than double. It's at 9,626. So let's write an exponential growth function. So we're using f of t, right? The y-intercept goes first. So you know what the y-intercept is. In this case, t equals 0. So we're starting at 100. Now, right, what's the ratio here? It's 130 over 100. Now, we could write 13 tenths, right? But that's not the way we've been writing them all through this lesson. How would you write 13 tenths as a decimal? Well, it's 1 3/10, or 1.3. Right, so this is 1.3 to the t. Right, now, if you do 169 divided by 130, you're going to get 1.3 again. Now, again, I rounded some of these numbers, and let me make sure that it comes out exactly that. 169 divided by 130. Yep, that one comes out 130. Now, if you do 219.7 divided by 169, yes, but there may be some rounding differences on some of these. If they don't come out exactly the same, it's because of the rounding. But you really only have to do the first one, because that one's usually the easiest. So do this one. There's our y-intercept. Goes first in an exponential. So we need 70 over 50. What does that equal? It equals 7/5, which is 1 2/5, right? Which is 1 4/10, which is 1.4. All right, now 7/5, right? You could also do 7 divided by 5. 5 goes into 7 once. 5 goes into 24, and got in it that way. Let's practice. So we're starting with 1A bacteria, so 1, and it's splitting 4. It's getting 4 times as much, so the ratio is 4, right? And so this is our function. So it's f of t, equals 4 to the t. So f of 5 equals 4 to the 5th power. So what's 4 to the 5th power? 4 times 4 is 16, times 4 is 64. 64 times 4, 256, times another 4. I'm getting 1,024. All right, so it's getting 4 times bigger, 4 times as many cells every single hour. And this is a word problem. I should probably write cells. I haven't been doing that. I should be. I wrote dollars when it was dollars. All right, so here, right, in the previous Twitter problem we did, we were doing it, you get 3 times as much. But what if your followers are growing at a rate of 60% per week? So this person has 500 followers now, so that's times 0, the beginning of the y-intercept. We're growing 60%, so we're going to be at 160% every year, or 1.6. And we want to do 10 weeks. We want to know how many followers we should expect in 10 weeks, right? And if you've been growing at 6, this is what all sorts of analysts are doing on their Instagram followers who are professionals at this. They're looking at the growth rate currently and then making a projection, and then 10 weeks later, if that projection is lower, right, your growth has slowed, maybe they need to take some action. Or maybe you're doing better than your projection, because 10 weeks later, you've got way more followers, and so you've been doing a great job. So let's do 1.6 to the 10th. And so that comes out as 109.95 approximately. Let me just double check that. So 1.6 and to the 10th. Okay, and then I have to multiply that times 500. And so if you're growing at 60% per week, 10 weeks later, you are going to have 54,976 approximately, I should be using approximate symbol, followers on Instagram. That's tremendous growth. Usually most things cannot sustain that kind of growth for a long period of time. But you can see how people get followers, a lot of followers, very quickly. So we're getting 4% interest, and we're going to leave it there for 40 years. So it's 5,000 times 4.80, and it's 4.8. There's a bunch of numbers after that. And so 40 years later, if you've left that money in an account, now it's $24,005. Way more. And you've done nothing but leave it in the bank. All right, we need the y-intercept where t equals 0. What's the growth rate here? Right. Well, that's 3/2 or 1.5, also known as 1.5. And so that's all you have to do.